Okay, let's go back to the situation of correlated input variables. So we said that often two variables may represent nearly the same thing, and this is called multicollinearity if the variables are input variables. Examples may be a person's height and weight. So height and weight of a person are fairly correlated, right? If you're taller, your weight will go up in general. Age and sales price of a car. So if a car is older, of course, the price will go down. And there's probably a pretty strong correlation between these two. Years of education and annual income. There's probably a pretty strong correlation between those two. And if these are input variables in our model, then this could be a case of multicollinearity. Now, multicollinearity is a problem for regression. It's not necessarily a problem for most of the other machine learning algorithms. Another example, you may be looking at contributions to a town charity organization using a model that includes the population of the town and the total gross income of the town. So total gross income, that means how much money does each person make times well, I guess I should say, if we take each person, how much do they earn, and sum up all the values of the entire town. So obviously it's going to depend, the total gross income is going to depend on the population, and there's going to be a pretty strong correlation between those two, between the population and the total gross income of the town. So that would be another example. So if this were a regression, we'd have to remove one of them. Okay, another thing to note is that, as we said, correlation of an input to an output is typically good, but not always. For example, today's stock price versus today's volume of trades on that stock. So maybe the volume, the number of trades on that stock is correlated with the price, but we wouldn't want to use this as an input into predicting the price. Why? Because this information on today's volume is not available before the price data. So if they're both coming out at the same time, we can't use one to predict the other. And that is an important thing to think about in all of the machine learning attempts that you make. So if one thing comes out or appears at the same time, you can't use it as an input variable. Now you could use the volume of trades on that stock from yesterday as an input into predicting today's price, but you can't use it today, the volume of today's stock trades, to predict today's price, because you don't know you might have it in your data set, but you don't know in terms of making a prediction what you won't have today's volume to predict today's stock price. Okay, let's take other opportunities when there is multicollinearity. So what can we do when we have multicollinearity? Actually, that can be an opportunity or something valuable when we have this multicollinearity, except when we're doing regression. Then we just have to get rid of it. Okay, here's an example. Suppose we have two variables. So in retail sales, we can think about the original order value versus the net order value. So the net order value is the total value of items ordered after taking into account returns and items not supplied because they were out of stock. So in other words, this is how much people ordered, but people might return some of their goods, or they might have ordered things that we don't have in stock. And so the actual net sales is going to be less than the gross sales. There are going to be some deductions that we're going to have to think about to get the net sales, right? What does it say? Some of the items are going to be returned and others were out of stock. Now we might have both of these columns in our data set. We might have a column for gross sales and we might have a column for net. And now, even though these are different, they are going to be very, very highly correlated. So if you have high gross, then you're going to also have high net, and vice versa. So in one sample of 50,000 customers, the correlation coefficient between these two was extremely high, 99.3%. if we drop one, so we typically would think about dropping one, and probably if we're going to drop one, this one we won't know what it really is until later. So there's some kind of lag here because we don't know what's going to be returned and so on. This we know immediately. So we probably drop this one and not this. But here we're not actually talking about dropping. We want to think about some other opportunities when we do have this kind of correlation between inputs. So, however, here we want to discuss keeping both of them. So the average of the gross was $196, but the average of the net was lower, and it was $187. So there were some returns and so on, which caused this to be lower on average. However, these averages conceal something interesting. For the vast majority of customers, these are going to be the same. The gross and the net are going to be the same. Most people don't return things, and most people probably don't order things that are out of stock. So basically, the gross and the net are going to be the same in most cases, or most rows of our data. However, just a handful of customers order thousands of dollars worth of merchandise, but they return it all. I'm not quite sure why they would do it, but they're certainly not the kind of customers we'd want. Both variables are needed to identify such renters. They're called renters. In the industry, they're called renters. So how do we identify it? How do we identify those transactions? Well, we said that in most rows, this is going to be identical to this, but there are going to be a few rows in our data set where this is going maybe only 1% of the, so 99% of our rows, this will be equal to this. And then in just 1%, this will be very different than this. So the gross will be very high, but the net will be like 0. Okay, so we need both of these though to identify which rows that would be. For which rows we would have a large number here, but 0 here. So we want to identify those transactions, those so-called renters. They're just, I guess what they're doing is they're ordering the stuff and using it for a month or something, and then when they have to return it, they return it, and they get full refund. So they got to use it for whatever period of time that was, maybe for 1 month. So they're called renters. A derived variable, the difference between them, will identify renters and will highlight this highly unprofitable behavior. So we can make a new variable which is simply the difference between this and this. And most of the time it's going to be 0, but sometimes it'll be a big number. And that will be, basically that will identify who are the renters. But in terms of our model, it will identify something very important to the machine learning algorithm. Now, of course, after we do that, we could delete these. Or rather, we probably wouldn't delete both of them. As we said, we'd probably delete this one. So we'd have this new variable and this one in our data set. So this is the calculation. We would take the gross minus the net, and we could call it renter indicator. And we would have our new variable. In general, when two things are usually equal, which these are usually equal, the few cases where they are not may indicate something of interest. Here, we saw and indicated the so-called renter phenomena. Usually when two variables are this highly correlated, one of them should be eliminated. But in this case, as this case illustrates, it's worth thinking about whether there's some way that both can contribute. Okay, let's consider another example, and this is where we're going to talk about the ratio of highly correlated variables. Last example was the difference between two highly correlated variables. So this is an example of, suppose we have a data set or a study of universities, and suppose we have two variables, the number of students and the number of professors. So those are two separate variables. So either of these variables is sufficient to determine if a school is large or not, and so there's no point in using both for that purpose. Now, these would be fairly highly correlated, the number of teachers and the number of students. However, we can consider the ratio of these two, so students per professor. So we might have 10 students per professor at one school and 100 students per single professor at another. And this is an important ratio that may vary independently of the institution size. And it's also a measure of the amount of individual attention a student can expect. So this would be a very good and useful derived variable. Okay, let's look at another example where we're going to talk about ratios of highly correlated variables. So another example where the ratio of highly correlated variables provides new information. Suppose we have two variables, amount paid and amount billed. So this is in the situation where we're like a B2B business, and so we're selling to other companies. So we bill out a certain amount, but they may not pay the full amount. So there may be a difference between the amount that they pay and the amount that we billed. Hopefully there's not, but probably there is. Nevertheless, these two would be quite highly correlated, right? If we bill out more, of course, we expect to be paid more. But this ratio shows the proportion of the billed amount that has been paid and can flag bad customers in a B2B business. So again, these are highly correlated. Okay, so we covered a number of important and interesting cases. And to do this in a programming language is very simple. So if you want to create a new variable and you have an existing variable 1 and another variable, existing variable 2, for example, you can just do this to get the new variable as the difference between them. Or if you have you want to do another one, second new variable, if you have an existing variable 1 and you want to take the ratio of that with the square of an existing variable 2, you can do it this way. And in Python, it's just as simple. Now, in programs like Weka or RapidMiner or other software data science packages, like in Weka, for example, there's an expression, there's a filter called math expression, and so you can use that. And when you look at it, this is the filter called math expression, and you see that you can give it a name here. Excuse me. This is the expression. So you can build a function like this. Here we have the given variable minus the min divided by the max minus the min. So that is what we call the min-max. And that will map everything to a 0-1 interval. And we have many different options. We can use all these operators here, power, log, absolute values, cosines, all of this stuff here. And we can also refer to the mean, max, min, and so on. The letter A refers to the value of the attribute being processed. Okay, so that's pretty easy to use. And in RapidMiner, it's also easy to do this. So here we brought in some data, and there's an operator called generate attributes, which will do the work for us. And you just click over here, and you can add an entry to add a new variable, and you can give it a name. I just did 2 examples here, but I'll do one more. Let's say new variable 3, and then you just click over here, and you can use the existing variables and then use many different functions and many different operators and so on to create a new function. For example, suppose, I don't know why I do this, but suppose I did age plus passenger class. That doesn't seem to make any sense. That would not be intelligent creation of variables. I wonder if I have to do this. Does that work? I think we need to write it that way, actually, or you can just click on these to bring them into the expression builder. Now, this would not be a good example of a derived variable, but this is how you would do it mechanically, and then you just click apply, and then you have this new variable. And then you click apply here, and you can run this and see all of these new variables. So the original variables in the data set are survived, age, passenger class, I believe it is, first class, yeah, sex, number of siblings, number of parents, then passenger fare, and this is number of related, which is just an extra one that I just created, which is just the sum of these two. So 0 plus 0 is 0, 1 plus 2 is 3, and so on. and then another one which is that new variable, this one, divided by age. So 3 divided by an age of 2 would give us 1.5, and then here is this other last variable that we created. It doesn't seem to make too much sense, but anyway, this is how you would do it in something like rapid minor. Okay, we just have a few more ideas to cover here. So the next one is starting with categorical data and converting the data to numeric. So here we have some data. We have maybe customer ID here, and we have their beer preference among 3 different Japanese beers, Asahi, Kirin, and Sapporo. So we can see customer 1 prefers Asahi, 2 Kirin, 3 Sapporo, 4 Sapporo, and so on. So this column here is a categorical variable or a nominal variable. It's not numeric, but we can do some recoding to create sort of numeric versions of this, and here's what we mean. Okay, so there's one approach which is called one-hot encoding. And what we do is we take every unique value in this column. So there are only 3 unique values. There's Asahi, Kirin, and Sapporo. And then the rest are just other examples of those 3. So we take each of the unique values and we create a 0, 1 variable for each of them. So I have a new variable called Sapporo, a new variable called Asahi, and a new variable called Kirin. And these are 0, 1 variables. So what I mean by that is the first customer, their preference was Asahi, so it was not Sapporo, and it was not Kirin, but it was Asahi. And the second customer, their preference was Kirin, so it was not Sapporo and it was not Asahi, but it was Kirin. And so on the third one is it is Sapporo, it's not Asahi, and it's not Kirin. So this scheme is called one-hot encoding, and we've taken this variable and we've basically replaced it with these 3. So this works if the number of unique values here is not too large. Here there's just 3, and it's fine to do this. But if you had, say, 1,000 different unique values here, it probably wouldn't be a good idea to create 1,000 new variables. This creates what is called sparse data. And in general, we like to avoid sparse data. Sparse data means where you have a lot of zeros. And here you can see we're going to generate a lot of zeros. And if we had 1,000 here, then in say the first row, and 1,000 different variables, 999 of them would be zeros. So you'd get a lot of zeros in that data, and we generally want to avoid sparse data or that kind of data. Now there's an alternative way to do this. So this is typically done in machine learning, but when you learn about regression, they do a slightly different version of this, which looks like this. And this is done by recognizing that we actually don't need this third variable. If we just specify Sapporo or Asahi, then we can imply whether it's Kirin. In other words, if you get 0, 0, that means it wasn't Sapporo and it wasn't Asahi, so it must be Kirin. So actually, I put this Kirin in here, but I could just drop this. I would just drop this, and I would only have 2 new variables, Sapporo and Asahi. But whenever we have 0, 0, that must mean that it would be Kirin. And if we had not 3 separate values here, but say 10 separate values here, and we did it this way, we would drop the last one, or drop one of them, and we would only have 9 of these columns. And these are called, in statistics, they usually call them dummy variables. So we introduce 2 new dummy variables here, or they're also called indicator variables. So we introduce 2 new indicator variables. So here in one-hot encoding, we introduce 3 indicator variables or dummy variables, but here we introduce just 2. Actually, we only need 2, but usually this is the way that's used in machine learning, and so you probably will do it this way. Okay, and then our last topic is doing the opposite, basically, and that is starting with numeric and converting it to interval data, which is more or less categorical. Actually, it's ranked categorical, or ranked nominal, ranked categorical. So let's say we have the familiar data set here. This is the iris flower data set, which has 5 columns. We have sepal length, sepal width, petal length, and petal width. These are characteristics of flowers. Like there's something called a sepal, there's something called a petal, and you can measure the sepal's length and its width, and the same thing with the petal. And so we have different flowers here, and then we have a categorical class variable or variable which we're trying to predict here. So anyway, these are numeric, but we can convert them to interval data, or essentially categorical data. So what do I mean by that? So let's work with this one and think about how we would convert this one. So if you look at this string, there's actually 150 rows in this data set. If you look at this data set, you can find the maximum petal length amongst all these numbers. It turns out to be 6.9. And if you can also find the minimum, and this length is spelled wrong, isn't it? And you can find the minimum, and the minimum is 1. So the minimum is 1 and the maximum is 6.9. So if we put it on a number line like this, we would need to go down as low as 1 and up as high as 6.9. So we have the number line here, and then we can just break this into intervals. So I could break it up here from 1 to 2, 2 to 3, 3 to 4, 4 to 5, 5 to 6, and 6 to 7. This is obviously not balanced very well, but excuse that. So, and then all you do is, so if this first one is, the petal length is 1.4, well, that's between here and here. So we call it, we say it's in bin 1. So we'd create a new row, which we might call petal length interval or something like that. We'd have a new row here. And for the first row, 1.4 was the petal length. Well, instead, we'll just say bin 1 here. And then we have another one here, 1.4. And so that would also be bin 1. And actually, all of these would be bin 1. But eventually, I suppose we would get some that are in bin 2 and bin 3 and bin 4 and bin 5 and bin 6. And there's nothing special about the widths of these bins. Here I created all the bins to have equal width, and I think I set up 6 of them here, but there's nothing special about that. I could have set up 10. Obviously the numbers wouldn't be as nice as this 1 to 2, 2 to 3, and so on, but you could certainly do that. And you could also, the bins don't have to be the same width either. So you can have like a wide bin for the first one and then a narrow bin, and they don't have to be the same. But anyway, that would convert this numerical data to basically these values here, which are not numeric. They're just names. And so that would be a way to convert numeric to categorical. Now, this is a little bit, could be a little bit of a waste, because here I know that this flower's petal length is bigger than this flower's petal length. So we have some information about the order, and we have some information about which is bigger than which. And that hopefully the algorithms, the machine learning algorithms, could take advantage of. Now, once we call them by names like this, bin 1, bin 2, bin, there's no order there. Now, you might say, well, this is smaller than this, but the machine learning algorithm doesn't know that. It just treats this as a name, this is a name, this is a name, and so on. So we lose all of that information here that we have actually in the original data. Nevertheless, this can be a useful thing to do. It can possibly improve your predictions. Why? Because you can use algorithms that you may not have been able to use before, and it may just be that those algorithms give you some better model. So in spite of the fact that you're losing information, it may turn out that you may get better predictions nonetheless. Now again, in programming like Python or R, you can do this kind of thing quite easily. And there are many options within the functions that do this, like whether you want the bins to be of equal length or not, and so on. And the same thing you can do in the packages like Weka and RapidMiner. I'll just show you in Weka. So here we have the name of the filter is discretize, because we're making a numeric variable into what we call a discrete variable. Basically means categorical. And sometimes this process is also referred to as binning the variable. So if you look it up in RapidMiner, you might look for discretize or binning. Anyway, here we would say which variable we're working with. So we were working with petal length. And you can say that bin range precision. Talk about the number of bins. You can, if you want, you can ask Weka to find the best number of bins, what it deems to be the best number of bins, if you don't want to set your own number. So in that case, you would, if you don't want to set your own bins, we would use bin numbers to false. And another option is to use equal frequency. In that case, what you're doing is, instead of having the bins being the same length, another option would be to choose to create the bins so that each bin has the same number of cases in it. So remember, we have like 150 rows here. So we're going to create bins so that maybe 30 cases are in the first, and 30 cases are in the second, and 30 cases are in the third. So in that case, we would only have, I guess, 5 bins, because 30 times 5 is 150. But anyway, you can ask Weka, but then the size of the bins will not be the same in that case. Okay, so this is just a list of a few of the Weka filters that will be useful in what we've talked about. So I think we already might have mentioned this one, and we mentioned the discretize. By the way, there are 2 discretize, and we would generally want to use the unsupervised version. There's also a center, and we talked about what centering meant, and the center filter will center the data around 0. There's a math expression, I think we talked about that, to create a dummy variable. Actually, no, it's a one-hot encoding. You can use nominal to binary, and we talked about normalize. I think I forgot one more here. So normalize, replace missing values, that can be useful, and standardize. So let's just take a look at a few of these. So here's the iris data, and we can see that the sepal length, varies from 4.3 to 7.9. Let's try the center filter. So here it is, and we can take a look at it here. So let's just use it, and let's see what happens to these values. So now you can see that it's centered at 0. The mean is 0. And this is the standard deviation, and this is the range of values. Now, let's just undo that. And if you check the standard deviation, it's still the same. So centering does not affect the spread at all. Okay, let's try another one. Let's try normalize. And let's take a look at what that does. It says normalizes all values in the given data set apart from the class attribute if set. And you can see these are the settings here. Ignore class false. I don't think, unless the class variable is, if the class variable was numeric, I guess this would apply it to the class variable as well. But since our class variable is not numeric, it won't do anything to it. Now, let's see what this is going to do. So you can see that scale and translation are set to 0 and 1. Let's just test it. Apply it. Which one we're applying it to? I guess this applies it to all values in the data set except for the class. Okay, so it's going to do this to everything, but we'll just check here, and let's apply it. Okay, so now you can see that all the data was mapped to 0, 1. So this is acting like the min-max normalization that we talked about. Now let's undo that, and let's just play with those numbers a little bit. Let's say we change this to 2 and change this to, let's say, 3, just to see what happens. Okay, and apply it. Okay, now you can see that it stops at 2, and the width goes up to 5. So that's what these parameters do here. Okay, but normally we wouldn't do that. We would say it should be 0, start at 0, and go only 1 unit in spread. So you would set it like this, like we did the first time. I guess I have to undo it first. And then is it still set to the same thing? Yeah. So now, again, I'll just apply it again. And you can see it's 0, 1. Let's see, it supposedly applies to everything, but they're all in the 0, 1 interval now. Okay, so let's undo that. And let's check standardize. Okay, let's see what the parameters are here. It doesn't give us any choices, but so the explanation is standardize all numeric attributes in the data set to have 0 mean, so it's centering it, and unit variance. That means it's doing the z-score normalization that we looked at, and we didn't mention it, but standard deviation of the z-score normalization will be 1, and that's what this does. It gives unit variance, or standard deviation will be a unit or 1. Okay, so let's try it. So this is not going to map it into a fixed interval. The spread is going to be, I should say the range is not going to be fixed, but the standard deviation will be only 1, and it will be centered at 0. So anyway, this is the z-score normalization. Let's apply it, and apparently it's going to apply to all of these variables. I guess we can't choose just one of them, but that can be nice because it makes it easy. So now you can see that the standard deviation has been changed to 1. Let's just undo that and make sure. What was it before? It was this, but now when we apply it, it's 1, and the mean is now 0, and the minimum and maximum are like this. And the same should be true. The minimum and maximum will not be the same, but the mean and the standard deviation will be the same. So we see that, and we see that, and we see that. So that is the z-score normalization that we talked about. Now let's just take a quick look at replace missing values. So it replaces all missing values, doesn't give us any choice as to what columns to apply this to, for nominal and numeric attributes in a data set with the modes and means from the training set. So what does that mean? Well, let's undo what we've done. So it's back to here. And let's take a look at our data. And let's say this was missing. So how can we do that? I think we can just delete it. Okay, so we'll delete it. And let's click OK. Let's see if that holds. Let's click on Edit. No, that didn't hold. Anyway, let's imagine that this was empty or missing. Not 0, just missing. Not 0. 0 is different than missing. But let's imagine that it was missing. So the question is, well, what if we were going to try and fill this in, what should we try to fill it in with? Now, there are many different sort of ideas about what we could do here or strategies, but probably the simplest is just to calculate the mean of this entire column and then replace this with the mean. I mean, it's not such a bad strategy, right? Just replace this with the mean. So that is what it does. Now, what about this one? So suppose this one was missing. So this is a nominal variable. So how should we treat that? So let's suppose there were 100 of the iris versicolor, and the other ones were all virginica and setosa, but there were a lot more versicolor than anything else in this column. And now suppose this is empty. So what should we replace this with? So if there was mostly versicolor in this column, then why not replace this one, which is missing, with the one which is most common in this column? And that's called the mode. So that's what this does. You can see it says replaces all missing values for nominal and numeric attributes in a data set with modes and means from the training data. So from the training data. Okay, so this is the most basic, I guess the most basic strategy for replacing missing values. Let's just quickly, suppose we had a nominal data set like this, for example, and here let's look at these values. This is the weather set. Now suppose there was one value missing here. Okay, so another strategy besides choosing the mode for this column might be to look at these. This is mild, high, false, and yes, and look for other cases where we have mild, high, false, and yes. Now in this tiny data set, we may not find any other cases like that, but let's see, do we have mild, high, false, and no? Mild, high, no. Anyway, we may not find in such a small data set a match. But if we had not just 14 rows, but say 1,000,000 rows, then we're definitely going to find many, many matches. So what we could do, a different strategy, instead of just using the most prevalent value in this column to fill in here, what we could do is just look at all the cases that match this. So all of the cases that have mild, high, false, and yes, maybe there's 1,000 of them. And then just isolating those, say, what's the mode for that data set, and fill in here. So that would be a little bit better than just the mode in general. So that's another strategy, but I don't know if there's a filter like that in Weka. There probably is something like that, actually. And let's just review math expression once more. So we can create expressions here, and you can learn about what these stand for, what min stands for, what a stands for, and so on. But I think we said this is the min-max filter as it stands right here, but we can change it. We have lots of other functions we can use. So we can do all kinds of transformations with this. But some of the basic transformations are already encoded in Weka as individual filters. Okay, so this topic that we've been discussing is called derived variables, or feature engineering. It means creating new features. And we've seen that it takes kind of insight. You need some insight into the data in order to create the new features, or at least to create the so-called intelligent new features. Now, some people do sort of the kitchen sink approach, which means they just sort of arbitrarily create different new variables and see if any of them happen to be predictive. But hopefully, you can also come up with some insight which will lead you to create variables that make some kind of sense. And we talked about what to do about correlated input variables. We talked about this example of creating a variable called seminar appeal. We mentioned that this is a kind of art side of data science. We gave the example of doing BMI, which is mass divided by height squared. We gave a second example, which was where we took the number of products sold and the cost per product and created a new variable called total sales, which was just the product of those two. We explained that these are just functions of variables. So this is one type of function, this is a different function. We gave some plausible reason for why we should use height squared. And that was because people are not like spheres, but they're also not like cylinders. So it's in between. This would just be height. This would be height cubed, and people are somewhat in between there. So it seems that height square works pretty well. We gave the baseball example where two new variables were created and led to a lot of success in the baseball industry. We had the slugging percentage, and we had this one as well. We gave the example of wind chill, and we saw that that contained both sums, well, actually differences, and also products. If you think of this as an equation, you have a constant times, this would be like x, and this would be y. So you'd have like ax minus by times cxy. Or maybe you would include an exponent in y. We talked about working with just a single variable and how we can transform it. We can center it. We can do centering and scaling, and we called that the z-score normalization. We also said we could map all the values into the 0-1 interval, and that's sometimes called the min-max transformation. Now, of course, you could create these in either Python or R or Weka or RapidMiner or other software, but there are examples, or actually filters in Weka that will do it. I'm sure there are filters in RapidMiner that will do it. There are functions in R and Python that will do it. So a lot of these standardizations are already created in all of these frameworks. In terms of correlated input variables and the issue of multicollinearity, we said that sometimes we don't want to just get rid of those variables or just get rid of one of them, because the difference between them, or the ratio of the two of them, can be insightful. And we saw that in this case we can identify renters. We had the concept of renters, or people that are abusing our ordering system. We saw here that even though the two variables, number of students and number of professors, could be highly correlated, the ratio still provides us with something which provides us with a measure of how much individual attention a student can expect. We saw this example where we consider amount paid and amount billed are also correlated, but their ratio can tell us something about our customers. We saw how to do this in different software applications and also programming languages. And finally, we talked about how to convert categorical data to numeric, and we saw that that can be done like this, and vice versa, how to convert numeric to interval or categorical. We could do it like that. This is called binning or discretizing sometimes. Okay, so what's the takeaway here? So the takeaway is that you should pursue your data. So you should think hard about your data and see if you can come up with some important new derived variables. It's the basis for all the results that you can produce. So coming up with that kind of insight can really improve the bottom line, really improve your accuracy, and in data science competitions, it can be the factor that allows you to win the competition.